Understanding digital interfaces. Now, analog interfaces may be a blast to configure. I have a great time with them. But when you come to a larger office, a single call per line just won't do it. It may be okay for a single phone that you have off here, maybe scattered throughout the company, but for our outbound PSTN connections, we'll need a larger interface capable of handling more calls per line. That's where our digital interfaces come in. And in this video, what we're going to take a look at is, first off, the CAS versus the CCS connections. Now, when I got into this voice over IP world, I learned a ton about these connections that I never thought I knew. CAS and CCS, I just figured, was the difference between a straight T1 and an ISDN PRI line. For years, that's what I thought. CAS equals T1, CCS equals ISDN PRI. But that is not it at all. We're actually seeing a lot of different interfaces that use CCS, even besides ISDN. And CAS has some inherent drawbacks that we have to make sure we know about before we decide to use it. Now, the second thing we'll talk about is ISDN. It's back. Everybody's thinking, oh, ISDN is gone. DSL cable modems are in. But ISDN is everywhere in the traditional telephony world. A lot of our PSTN connections will run on ISDN. A lot of our PBX to PBX communication will run on ISDN. But ISDN is just one flavor of something known as CCS. We're going to take a look at all these different protocols, QSIG, DPNSS, SIGTRAN, and SS7. All these protocols that are very similar to like TCP/IP, IPX/SPX, AppleTalk, NetBEUI. All these protocols from our network world, these are similar in the telco world, signaling protocols that can be used between PBXs. We'll talk about which ones are in use, which are more widespread, why one might be used over other. You will be digital interface experts by the time this nugget is done. So let's get going. The first thing that we need to look at on our digital connections is the two major umbrellas of connection types. The first one is something known as CAS, which stands for Channel Associated Signaling. CAS sends your signaling information with the bandwidth of your user data. Now, I know that's kind of a mind twister if you just take it at face value. So the first thing I want to do is define what I mean by signaling. When I say signaling, what does that include? Well, signaling is everything but the actual audio stream that's being sent. For instance, if I pick up a phone and dial 12345, those dialed numbers that I sent, DTMF, dual tone multi-frequency, tone dialing is considered signaling information. If I send caller ID information across that line, that's signaling. If I push the hold button or implement a conference call, that's signaling. Anything but the actual audio is considered signaling information. And CAS will squeeze that signaling in along with the same pipe of bandwidth, the same audio stream that's being sent that sends my voice. The actual words that are coming out of my mouth being digitized and sent are squeezed in there. Because of that, this has earned the name robbed bit signaling, because it literally robs or steals bits to send the signaling information. It's immoral signaling. We have every 6 bit from each frame is stolen to be sent. Now, with super frame signaling, this is kind of an older form of signaling, you would send a burst of 12 frames at a time. You would send, on your T1 line, 12 frames, poof, in one big burst. And out of those 12 frames, we would steal 2 signaling bits. Now, the most common standard that people use nowadays, it's a more efficient way, is known as extended superframe, which instead bursts all 24 frames at a time and allows 4 signaling bits inside of there. Now, we're not getting, a huge advantage from extended superframe other than efficiency, because we do have just as much signaling information. It's just this sends 12 frames at a time, this sends 24 frames. So we double our signaling. Now, when we use CAS connection, it means the advantage is that all channels are available for data. So on a T1 line, we have 24 64 kilobit per second channels. That's also known as 24 DS zeros. That's how we divide up our T1 lines. all of those will be available for use. So I can receive 24 incoming calls or make 24 outgoing calls to the PSTN or some variants thereof. Now, the disadvantage of this is since you are literally stealing bandwidth from your user bits, the overall bandwidth you have for data is reduced. And what that means is on a lot of our data connections, like our modem lines or our fax communications, sometimes our speed will not be as good as using a CCS connection where they totally separate the signaling from the bandwidth. So in this world, you'll see a lot of people say, hey, you know, we hate CAS, and a lot of those will be your modem users because they want to have higher speed connections. But nowadays, we don't use modems as frequently as near as frequently as we used to in the modern technology world, and fax communications can be squeezed across CAS lines. So what usually boils down is if the other side is using CAS, if the PSTN uses CAS connections, we'll use CAS as well. Now, inside of CAS, and this will start getting into the configuration when we get to the next video. I'll show you how to configure these. Inside of CAS, you have a lot of signaling types that you can use. I mean, don't think of CAS as the actual signaling. When I say CAS, I'm not actually referring to a type of signaling. I'm just referring to a way that we do signaling. For example, I can choose FXS on top of CAS. And now you might think, whoa, whoa, whoa. FXS, that's an analog port, right? FXS connects to an end phone. Well, yes, it does, but we can also configure FXS signaling to work across the CAS line. Think of it this way. I mean, when you pick up your home phone, you know, you pick it up, you know, I've got my phone right here. I picked it up, I dial 113. You know, I'm dialing this phone. What kind of signaling do I have? Am I sending, you know, certain kinds of signaling across there? No, it's all considered in-band signaling. My home phone uses in-band signaling. I don't have a separate channel that I have for signaling. So I'm using a type of CAS even on my home phone because all the signaling is transferred in-band. So we'll see on top of CAS many flavors of signaling that we can use. The other major umbrella of digital connections is known as CCS, which stands for Common Channel Signaling. Now, unfortunately, I wish I could think of a way, because I've tried for years to think of a way to remember which one was which, CAS versus CCS. The only way I can remember it is, I think, CAS, Channel Associated Signaling, meaning the signaling is associated with the audio channel. With CCS, we have common channel signaling, which means all our signaling is in a common channel. It doesn't share the bandwidth with the data. So what you do is you literally carve out, you see my green channel here, I carve out a single channel that I dedicate to all my signaling information. The advantages of doing this is that I do end up with more signaling information. I have a larger chunk of bandwidth, I guess you could say, dedicated to just signaling. Now, if you added up all the bits of CAS, it would typically end up coming around to about the same amount of bandwidth as CCS. So CAS and CCS gives you nearly the same, but this dedicates a common stream. And that means that we have more protocols available to us that can fit into this channel. Essentially, this will be, on a T1 line, a 64 kilobit per second channel that I can use solely for my signaling information. And this means that none of my user bandwidth is used. Each one of these other channels right here, the red channels, are all dedicated to nothing but audio, which means all 64 kilobits of that bandwidth goes to the audio. Gives me higher performance modem and fax communication connections, and ensures my voice quality when I'm getting into voice over IP. Now, the disadvantage of CCS, and this, I know I've been talking about T1 lines, but this same thing applies to E1 lines if you're over in a country that uses E1 style connections. Disadvantage is you lose a complete channel. If you purchase a T1 line using CAS, I have 24 channels at my disposal. With CCS, I'm down to 23. So that means 23 channels can be used for incoming and outgoing calls. With that being said, most PBX connections that you're going to encounter will have CCS style connections. Now, I know a lot of you immediately, if you're like me, if you're thinking back to the days of data, when you think CCS, the only thing that you think about is ISDN. Now don't get me wrong, ISDN is a huge protocol that can use CCS technology, but it's not the only protocol, especially when we start thinking about the telecom terms. What we're used to seeing ISDN as data people, is the two major flavors. We see the ISDN BRI, the basic rate interface, and ISDN PRI. Now, when you say ISDN BRI in North America, people are just kind of like, yeah, BRI. Well, you know, that's gone. We have DSL. We have cable modems. But BRI connections are still huge overseas, especially in Europe. They have BRI connection. Australia uses a ton of BRI. Trying to think of just pretty much that whole continent of the European continent. Now, it's not uncommon over there to see cards like this installed inside of a PC. You have a PCI card that can accept a straight ISDN connection and can handle data calls or data interfaces from that, internet connections and so on. And that's because this graphic came from ISDN years ago. ISDN was designed to be the ultimate transport, transporting voice, video, and data across a single medium. And it's kind of funny that Cisco came out with Cisco Avid, architecture for voice, video, and integrated data. And everybody's like, oh, Avid, the new strategy. But, ISDN has been doing this since the early 80s. So it's it's a reuse strategy. It's like a trend cycle going around again. So BRI connections, you have your 2B channels, and those are 64 kilobits per second each, our standard data transfer, and one D channel of 16 kilobits per second each. Most of the time you'll see it as 2B plus D. 2B or not 2D. Anyway, so this allows you to have your 16 kilobits per second of signaling. You don't need that much, a full 64K channel, since you only have two bearer channels or B channels. Now, PRI is still in use everywhere. This is a huge form of ISDN, and this is where we have the 23 B channels plus the 164 kilobit per second D channel. And this is where most of us see our T1 connections coming in CCS flavor. Now that's going to be where most of us data people leave off. And you may have heard of Q.931 and even Q.921. And when the data person thinks of this, they think, oh, debug commands. If I have a problem with ISDN, I have to debug Q.931 to start troubleshooting and finding things out. But Q.931 is the signaling protocol of ISDN. When you think of Q931, think of that channel. Remember that grid I had drawn up where we had all those 23 channels? That first channel, it's like the TCP/IP, or the IP, if you will, of ISDN that does all the signaling. But instead of handling IP addresses and port numbers and things of that nature, this handles things like forwarding, call forwarding, when I forward a call. Call hold, call transfer, DNIS, and ANI. These are our two forms of sending dialed number and caller ID information. DNIS stands for the Dialed Number Identification Services. This allows, if, for instance, I have a router right here, or you know what, we're telco days, right? We've got our PBX right here connected to the cloud of the PSTN. Okay. When the PSTN sends a call into our PBX, it allows the dialed numbers. I mean, the person who dialed these numbers out here to reach your business, they had a phone and they dialed, 1-800-555-1212, goes to the PSTN, it will actually send the number that they dialed, the dialed number identification service, 1-800-555-1212, into your PBX system, so your PBX can see what number they dialed. Now, the reason that's useful, at your home phone, that's not really useful because you only have that single line coming in. But for a PBX, that's useful because they have this concept called DID, Direct Inward Dial. And that allows this person to dial 555-1212. It comes into your PBX, and your PBX can send it straight to whoever extension 1212 is. Because maybe you also have a whole block of DID numbers, 555-1213, and that goes to another phone over here. So it eliminates the need for a receptionist to route the incoming call, because the dialed number can be sent to the PBX and it routes it on. Now, the ANI is more commonly known as caller ID information. It stands for Automatic Number Identification. That allows you to see who the person is that is calling into you. all of that information is transferred using that Q931 signaling protocol. And it's kind of funny because me coming from the data world, I always thought, oh yeah, Q931, that's the layer 3 ISDN protocol. I debug it if there's a problem. That's all I really cared about. But now as we're into the telco days and we're looking at how to get data between our devices in the telecom system, Q931 comes alive to me because I go, oh, this is where all my features come from. This is how my PBX is able to transfer a call and not lose it. This is how I can send the caller ID information. And this is also if I am sitting at a phone and I see it ring and I'm not receiving caller ID information, this is the first place I look. I go, oh, something's going on with my Q931 protocol. The difference in the telco world is it doesn't stop there. The Q.931 protocol is just one of many protocols that could run across that CCS transport. The number one most popular protocol that you'll encounter is something known as QSIG. Now don't try to go find the definition of QSIG on the internet and what it stands for because you won't find anything. QSIG is an acronym without a definition. It just stands for Q signaling because it was based on the ISDN Q.931 signaling at layer 3. And here's the problem. When PBXs were really starting to emerge in private businesses back in the day, in the early 1980s, we had a problem. Because let's say we had a PBX from Nortel. Nortel would make their own signaling protocol and would allow, Nortel PBXs to link up to Nortel PBXs. But let's say we bought a Mitel, that's another vendor of PBX, a Mitel PBX over in this location. And this was Michigan, and this was Arizona, and this is all one company, 2 locations. Well, in the early 80s, when this was really first starting to emerge as a private way of running your own phone system, the problem was there was no industry standard protocol that these could use. I could buy that tie line over the telco to link these two directly, but they wouldn't have a common standard to communicate. Nortel would only be able to talk to Nortel, and Mitel would only be able to talk to Mitel. Thus, the need was created for a vendor-independent protocol, and that is what QSIG emerged as. It came out in somewhere around 1981, and it allowed PBX to PBX communication. This is known as the Private Internetwork Exchange, or Private Interdependent Network Exchange. But it pretty much allows other brands of PBXs to communicate amongst each other. You can think of QSIG as the telco form of TCP/IP. I mean, if you think of TCP/IP, it allows Cisco routers to talk to Nortel routers, to talk to Windows PCs, to any different devices. But did I just say Nortel routers? Okay. So we have these, these different brands of routers that can communicate because TCP/IP is vendor independent. That's what QSIG is for the PBX world. Now, instead of just keeping this in all theory, let me tell you why these protocols are important. It's because we're going to see a move from an environment like this, where we have the PBX systems linked up across the telco, to an environment like this. Whoa! I need like a cool sound effect right there. Whoa! Because the routers just plopped into the middle, and what happened to the telco? It's gone. The telco has evaporated. Well, it's still around, but it's now just to backup connections. Our routers will have the ability, or I should say do have the ability, to transport QSIG information from that Nortel PBX that, we still have a need for, so it's not going to go away anytime soon. So we have our Nortel PBX system over here communicating with the Mitel system over here, but now there's a router in between that has a T1 PRI interface going on right there, and a T1 PRI interface going on right there, and it's acting as a proxy between these two, transporting all those packets over the IP WAN. So now we have QSIG as a protocol that's available for us in our tool belt of protocols that we're able to use to link up our routers, our Cisco devices, to the PBX systems. Now, QSIG may be the most popular protocol up at Layer 3, but we also have DPNSS. That's right. James Bond did play a part in developing DPNSS. It was actually developed by the British Telecom back in the 1980s. actually the 1980, the year 1980, before the ISDN standards were released and before QSIG came along. Believe it or not, this may sound funny, but the folks in the United Kingdom were a little bit impatient. They knew that the new standard was being developed, QSIG. However, they kind of jumped the gun and they said, you know what, we're tired of waiting. We're ready to go. We need this standard now. We'll develop the Digital Private Network Signaling System. What this does is allow PBXs to communicate features through the signaling channel just like QSIG does. It's essentially the same protocol as QSIG, but not based on the ISDN standards. Because of that, you'll see a lot of interfaces in the United Kingdom for PBXs still supporting this DPNSS. Now, you will not see, most of the time, unless you imported one, a PBX in the United States or even in Europe that supports DPNSS. The reason I bring this up is because a lot of times you may be trying to bring up a link between the United States and the United Kingdom and maybe some other part of the world over voice over IP, because international toll savings is where that savings is really realized for long distance. If you are interfacing with a PBX in the United Kingdom, chances may be good that you have to use the DPNSS protocol. If you're talking to a service provider about signaling, you'll often hear the signaling protocol SS7. Now, a lot of you may have heard this one already. SS7 is the protocol that was developed in 1981, defining out-of-band signaling between the telco central offices. So out there we have tons of telecoms. We used to have US West, now Quest, and we have MCI and Sprint and all these different telco providers. But in order for all of those different COs managed by different agencies to communicate calls between each other, they agreed on a common protocol called SS7. Now, this is primarily used between the central offices to send a call, maybe a long-distance call from your local carrier off to the long-distance company and back down to a local carrier in another region. However, you may see some PBXs that integrate straight into SS7 as well and can handle SS7 signaling from the PSTN. They're usually the very large PBX systems that would typically be used in a central office of some sort, but maybe a company has grown so large that they use one of these PBXs inside. Now, the reason SS7 is important to us as network technicians working with voice over IP is because our Cisco routers support a protocol called SIGTRAN. SIGTRAN is an industry standard way of communicating SS7 over a voice over IP or an IP-based network. It encapsulates SS7 packets inside of IP. Where SIGTRAN is starting to be seen is in the service providers. One of the major jobs that I'm doing right now is I'm working with a long-distance carrier to completely gut, it's called their switchless network, to their old telco equipment that allows them to provide long-distance services to their customers. I'm working with a service provider who is typically working with large business customers who would sign up for big bundles of long distance for their company and pay 2 or 3 cents a minute. And they're completely replacing their entire infrastructure with voice over IP. Because all the major carriers of the world, the AT&Ts, the Sprints, they now offer voice over IP services to large long-distance carriers. Now, it's a strange hierarchy in how it works, and it wasn't until I started working with this company that I really started to see it. You have, let me just show you how the telecom world works. You would have, for instance, the big players. Hang on, let me switch my pen here. The big players like the AT&Ts, the huge companies, the Sprints, all of these other major players up here. Those are just the two I can think off the top of my head. MCI, another major one. And they will, choose to interface primarily with kind of subsidiaries. You would have these smaller companies that would choose to interface with the customers. It's kind of like if you wanted to buy a Cisco router, you wouldn't go to Cisco and say, "Hey Cisco, give me a router." Because they would say, "Who are you, small little peon flick?" And they'd flick you off to one of their distributors. So you would have to go to someone like Insight, who buys in bulk from Cisco. And it's the same sense. In this case, we have MCI, who's the major player, and they'll have these subsidiaries, these nameless companies down here that you as a corporation, if you wanted long distance service, will choose to go with one of these subsidiaries that interface with one of these larger carriers. And a lot of times these subsidiaries will have multiple
connections to all these other carriers and use the one that gives them the cheapest rate. They're kind of like a broker for long distance. Well, what I'm seeing and what the one I'm working with right now is actually one of these subsidiaries. They're gutting their entire network, their switchless network it's called, and putting in all voice over IP systems. Now those voice over IP systems can link to each one of these carriers. Most of the time they'll be using the 58XX series routers. Those are the voice gateways that will support protocols like this, the SIGTRANs and so on. And they'll use least cost routing, meaning the carrier that gives them the cheapest long distance voice over IP rates will be the one that they route the call to. Because of this, they're able to offer typical long distance. I mean, they can use, for instance, a protocol like QSIG right here to communicate with the PBX or one of the ISDN standards to communicate with the carrier right here and convert that to SIGTRAN, which sends that information over to these carriers. In essence, it goes down from, say, a nickel or 4 cents a minute down to 3 or 2 cents a minute for this customer, because now this broker right here is paying less than a penny a minute for long distance using a voice over IP connection to these carriers. So that's primarily where you'll see SIGTRAN is inside of these companies communicating straight to the PSTN carriers. Isn't this cool stuff? It's like a whole new world of protocols is open to the network technician who's used to only dealing with TCP/IP. So to show you back on our Cisco routers, our normal Cisco routers that aren't, telco equipment like that 5800 voice gateway systems will typically support this slew of protocols. And I'll get into the configuration of these a little bit later. But on our analog, and this is, I'm talking connecting to the PSTN and PBX signaling. You notice FXS is not in here because FXS doesn't connect to the PSTN. It connects to an end user phone. So for the analog signaling, the in-band analog, you support ENM and FXO on your Cisco router. You can buy ENM analog interface and FXO analog interfaces. If you choose to use a T1 line and configure it as a CAS connection, meaning it's using the in-band signaling so you get all 24 channels, you have the whole slew of ENM signaling, which require a specialized interface on the PBX, or if you don't have a specialized interface on the PBX, you can use FXO or FXS signaling on top of that T1 CAS. Now it may sound weird to have FXS signaling running across the T1 line or FXO, but it's just a signaling type that allows you to use ground start or loop start, our same analog styles of signaling, to communicate with a PBX. And essentially, it'll be a on-off relationship. If we are using FXO on our Cisco router, that will most likely connect to an FXS signaling interface on the PBX. Now, if we're using FXS on our Cisco router, that will most likely communicate with FXO on the PBX. Now, there's ways of tweaking that and going beyond that, but that actually gets into that Gateway Gatekeeper course where you truly talk about a lot of the PBX integration and so on. And when we get into the configuration in the next video, I'll go over a lot of these signaling types and how to configure them, what might be some of the advantages of each. Now, if you are in Europe, there's two major types of signaling you have with your E1 lines, MELCAS and R2. And again, it's just a signaling type that we're going to configure for our PBX. Our PBX will support MELCAS or R2, and so will our Cisco router to be able to communicate. On top of that, if we choose to use CCS configuration, we can use it in the form of T1 and E1 ISDN Q931, and that's using ISDN because a lot of PBX and PSTN connections will have ISDN Q931 signaling. But even more so, you'll see T1 and E1 QSIG basic signaling. This is just the major flavor of QSIG that's out there. That is pretty much the, I guess you could call it the Ritz cracker. It's the very bland flavor of QSIG that should be compatible with nearly all QSIG implementations. So that will allow our Cisco router to communicate using a CCS channel, where it's that dedicated signaling channel, using QSIG to any vendor's PBX that supports QSIG. I know this video has been a lot of theory, but we're about to take all of this theory and put it into practical use as we start configuring our digital interfaces. But to wrap up, what we saw was CAS versus CCS. Again, CAS being channel-associated signaling, where all of our signaling is included in the same channel as our audio. We get to use all 24 channels by doing that. CCS is using the dedicated signaling channel, and you have some advantages of that, being that we have our ISDN signaling. You know, my ISDN, it's back. You can use that. But we also have the whole gamut of signaling protocols down here that we can use on top of that. Each one of these signaling protocols fitting its own specific niche. QSIG being the most popular one, integrating with PBXs and allowing our Cisco router to communicate features with the PBX. DPNSS for British Telecom PBXs. SIGTRAN to communicate SS7 over a voice over IP network. And SS7 being the protocol that's used between telco service providers. I hope this has been informative for you, and I'd like to thank you for viewing.